So these are the wonderful co-authors of this paper, and I believe some of them are here if they are not playing hooky this afternoon. But however, the first author, Ravi Bhoraskar, who deserves much credit of this work, couldn't be here today. Okay, third-party components are commonly used in mobile applications. For instance, AdMob is integrated with over 30% of millions of Android apps. And Facebook Connect is like one of social media plugin, is integrated with over 12% of Android apps. And other popular components of third-party components include analytics like Flurry or social gaming network and Amazon API. So why are they so popular? Because these third-party components, they make it easy for app developers to add new functionalities to their apps, right? But this convenience comes at a cost of security risks. So this first article that talks about an advertisement module that has an insecure update mechanism that can be exploited to compromise the whole app. And this last year's USENIX security paper, it talks about these vulnerabilities associated with single sign-on SDKs, such as like Facebook Connect. And there was a paper this year here showing that many websites are still exposed to these vulnerabilities. So, and then also, like the way that the first speaker pointed out, there is no privilege separation between these third-party components and then application code. So these the vulnerabilities that are introduced by third-party components can compromise the entire applications if that's exploited. So what can we do? Brahmastra. Okay, so our research goal is to enable third-party component integration security testing at scale, so that we can help App Store operators and also these third-party component developers sort of test those large number of apps and identify vulnerable apps for a fix. And specifically in this work, we are aiming to build a tool that supports test cases that need to be examined at runtime. And you will see soon why this runtime testing capability is important. Okay, so if you need to leave early, I mean, this is a beautiful like Friday afternoon, then these are the key takeaways of our work. So first, we built a testing tool called Brahmastra that enabled us to test almost 3 times more apps than the state-of-the-art GUI testing tool. And using the Brahmastra tool, we looked at 220 Android apps that are directed at children and found out that many of those apps displayed advertisements that were inappropriate for children. And we also tested 200 popular Android apps with Facebook Connect and found out that 13 of those apps were still vulnerable to this Facebook access token attack. Okay, so let me begin with one real example demonstrating sort of technical challenges of this test automation. So the last year's USENIX security paper that I showed a few slides ago discussed this Facebook access token vulnerability that can be exploited by attackers to steal users' sensitive data from an app server. So let's say you have an app, and then to test whether this app is vulnerable to this attack, you need to first sort of open an app and navigate through it to open Facebook login page like that, and provide login credentials once you get to this page. Then click login, and then while this client component of this thing and Facebook and app server, while those are communicating, you need to examine network messages to see whether this app is vulnerable. Then you might say, okay, so then why not use monkeys? Okay, so raise your hand. How many of you heard monkey testing? Okay, I would say about half. Well, basically, this monkey testing is just a tool, or also technique, that generates random UI events such as like clicks and keystrokes, so that you can exercise an app, so that people don't have to click through to make their app running. Then why not using these monkey apps? I mean, that sounds convenient, and then it should work fine. The problem is, there's been some recent efforts to make this monkey testing smarter, but still this monkey testing suffers from poor hit rates, like low coverage, code coverage, because mobile apps, you have all the smartphones, right? The mobile apps those are getting very rich with many UI elements, and also they require personalized information. And with kind of very rich UI interactions. So it's really hard to sort of simulate all this. Okay, so let me show you one example. So this is an app, right? So so remember that the goal is to find and click Facebook login button. And let's imagine that we had a super smart monkey, which is you. Okay, so here, what would you do to find a Facebook login button?
I agree.
Good. So click I agree, and then that will make this app transition to this next page. So this is a pregnancy tracking app. And then, if you're human or super smart monkey, then you look at this and say, oh, okay, so you need to type in your due date, which has to be a future date of today. Then, and then you have to put some name, and then click done, right? And that will make it transition to this page. So what would you do to find a Facebook login button? Anyone? There are some buttons here. What would you do? Okay, I think I heard some settings. Okay, so you press settings button over there. Oh, let me see whether I can enable laser printer here. So here's the settings button. And then it will move to this page with lots of buttons. I mean, it says you have to scroll down to see all the buttons. Then what would you do? Great. You guys are indeed smart. And boom, now you have this login with Facebook button, and then it's straightforward. Click it, and then do this, put some pre-made credentials, and press login, then that's it. So, I mean, one way is to make this kind of random monkey smarter, but that, like you have just seen, that will require solving very hard AI problem, right? So instead of doing that, in our project, we decided to leverage the structure of Android applications, and using only this structure and then page, so the way that the pages are connected to find this execution path to test these apps. So first, we characterize this Android app by statically building this page transition graph and call chains. And then instead of relying on these user events, we rewrite an app so that the app automatically navigate to those target page. And let me show you how. Okay, so this kind of illustrates kind of space of those pages that monkey would have explored if it had not been smart, which is the case. And in our case, so we first analyze those apps and then look at all those pages and how those pages are structured. And then we first look at, so we have to start with this target method. And in this case, this Facebook.authorize, so that's our target method. And then we statically find out which page invokes that API. And we call that our target page, which is this. And then from the graph, we prune all the pages. We first prune all the pages that cannot reach to that target page. So that will reduce this search space smaller. And then we do further optimization So since we can rewrite an app to do some navigation itself, we don't have to start from the first page. So here, in this case, we start from this node here, so that we can only sort of explore this small space. And then from here, we can further narrow down this search space by instrumenting the app so that it follows the shortest path from the start page to the target page. So essentially, that's what we do in Brahmastra. I mean, it seems like magic, right? But it involves a lot of sort of dirty tricks to make that work. So the part that does static analysis and then build these call chains, we call execution planner. So like I said, we first find these target activities. I mean, that's relatively straightforward. And then the hard part is to construct these call graphs and then activity transition path, and then get those call chains. Okay, let me sort of illustrate this. I mean, you can look at the paper for details, but basically this is how the call graph gets constructed. So here, this is, again, a one real app. And those ovals are methods, and rectangles are classes. And this one is our target method, Facebook authorize. First, we connect those methods that sort of, just look at the code and find, which method calls which method. I mean, this is a kind of very straightforward static analysis. So those synchronous calls we first connect. And then the hard part is, the colored edges. So there are, those page transitions happen through those intents. So there's intent gets created, and then there's a start activity. Call is made with that page URI. So we parse those, and then we connect those edges. So here, in one example, when this unlike clicked method is called, and that method gets transitioned to this next activity, so here. So we connect those edges. And then lastly, we look at those callbacks that were triggered by user events, like clicks and those things. So those clicks and those user events, that usually sort of trigger some other calls. So that we sort of look at the code, and then those relations are also linked here. So we have this call graph, and then once we have this call graph, from this target method, we backtrack and then create this path. So with this path, you can reach this authorized method. Oh, and then that part is integrated into this Redexer system, and it's open, so you can download and play with it. And once we have this path, and then we use this execution engine to rewrite app, so that once you open an app, then it just makes an auto transition to the target activity. So we built this, and we test it to see how our Brahmastra works against this state-of-the-art monkey called Puma. It's like a zoo, right? Puma and monkey. Okay, so how well does it work? Well, so Puma, the state-of-the-art monkey, so out of 1,100 apps, 13% it was able to reach the target method, whereas with Brahmastra, we were able to invoke this target method like for 35% of apps. And then, yeah, it's just still, we're better, but still the hit rate is a bit low. And then there are some reasons for that, and then we have details in the paper. And then test speed, obviously, since we only sort of look at those paths that are related to this target method invocation, it's much faster. And then using this, so what do we do? So first, we looked at those apps directed at children. Why? I mean, there is a recent update to this COPPA, Children's Online Protection Act, that says that mobile apps should not collect personal data without first obtaining parental consent. So to test this, we first, so these are kind of two specific test cases that we created from this reading this kind of regulation. And so basically this is the testing procedure. So with Brahmastra, we find a way to invoke this page that loads ad API, that loads ad, and then collected this banner and then landing pages. And then we used Amazon Mechanical Turk and then Web of Trust to analyze the content of the ads and the landing pages. And then with analysis, we found out that many of these apps that have landing pages, that have ads that point to landing pages that attempt to collect some personal data. And then, fortunately, many of the apps that we collected, the Mechanical Turk, they said, they classified those content as those types that are deemed inappropriate for children. And there are some examples here. And then, so with a similar technique, and then using Brahmastra again, we looked at 200 apps and then checked this against this Facebook access token vulnerability, and then the detail is in the paper. Okay, to summarize, by leveraging this application structure, we are able to create this tool that allowed us to efficiently test those third-party components' behavior within an app. And using this Brahmastra, we tested 220 apps that were directed at children and found out that those apps displayed ads that seemed inappropriate for children. And then again, so using Brahmastra, we looked at those 200 popular apps with Facebook Connect, and found out that 13 apps were still vulnerable to this access token attack. And then on the day of submission, we communicated with the Facebook security team and with this list of apps, and we got a response right away saying that those affected developers were contacted with an instruction to fix. So that's great. And with that, I'll conclude and take any questions.
Thanks, Jen. Please go to the mic.
Will Ank, NC State. Great talk, thank you. It seems like the benefit of this technique is that it's a goal-driven test generation tool. And so it seemed a little unfair to compare it to Puma, which isn't goal-driven, right? And so you were searching for a very specific part within the application, and that worked for Facebook. Mm-hmm. But then when you went to do the ads, it wasn't really a specific spot. And so how did Puma compare to you on the sort of the ad?
Oh, that's a really good question. So the ad part, it was, so we first looked, so ad part, there's a third party, you have to sort of load this third party package, and then there's an ad loading method that you have to call. So we use that as a target method, and then get this auto navigation to invoke that page. So that way we use the same tool to test this ad inappropriateness. But kind of comparing our tool against Puma, yes, there is some case that, so these Puma types of tools, like monkey types of tools, they were designed to increase code coverage, right? So, sure, they'll do fantastic in that way, but for this kind of goal-driven testing, they had weakness. So.
Hello, Theodore Boat from Rice. Great talk. But one question for you. When you're using an automated tool to click on ads, it seems like that's driving, money from the advertiser to the app developer and costing them money. Did you try to minimize that, or was that just sort of a consequence of the testing process?
Well, guilty. So yeah, maybe that's violating terms of service. I don't know. But we were just, we kept loading ads because we needed to collect many samples of ads. So we did it for a week time period, just keep running these apps to collect more ads, URLs, and so on. So probably those developers got some benefit from our testing.
Thank you.
Mm-hmm.
I have a question too.
Oh, Ben.
So can I write an app that tricks that knows that it's running under Brahmastra and can crash, for example, to foil your analysis of it at runtime?
So we rewrite an app. So if you write an app that resists from rewriting, sure, that could fail out.
I don't know how to do that.
Right. I mean, our technique won't work.
Great. Let's thank Jaeyeon.
All right. Thank you.